All right, today we're going to be looking at Chapter 4, Section 1, Scatter Diagrams and Correlation. Our objectives are to draw and interpret scatter diagrams, describe the properties of the linear correlation, compute and interpret the linear correlation coefficient, determine whether a linear relation exists between two variables, and then explain the difference between correlation and causation. So we have a couple of definitions. These are good to write down and keep in a notebook. You have a response variable. This is a variable whose value can be explained by the explanatory variable or the predictor. So they have an example down here. One thing we could say is the price of a car and the mileage if we're talking about a used car. So the mileage might explain or predict what the price might be. The response variable would be the price of the car, but we do know there's other factors that determine the price of a car. So you got a scatter diagram, a graph that just shows the relationship between two quantitative variables, so variables that can be measured numerically. The explanatory variable is plotted on the horizontal axis, response is on the vertical axis. So here's an example down here that measures two quantitative variables. It's about golfing, so a good read, and it could help you get a little bit more understanding. So they give you a little scatter diagram of, what club we used to hit the ball and how far it went. So the club head speed, and it gives you some information that they hit it on a day that wasn't windy. To eliminate some of the other factors, they use the same golfer, and of course, a person's strength, experience, and different things would affect, but they try to minimize all of those, and this is what we got. So what you notice is generally a positive trend, and that would indicate a positive correlation. So here are some diagrams that kind of show you some scatter plots that might have some relation. So this first one has a linear. It tells you at the bottom this one is linear. One's positive, one's negative. This third one is curved. It's nonlinear. This one is nonlinear, and then this last one it says no relation. It's linear. It'll be a straight line, but there's no relation. Now this one tends to trend more positive, but you can see the pattern is not linear. So then we talk about positively associated. So basically it says above average values of one variable are associated with above average values of the other. Simply that is to say the two variables are positively associated whenever one variable increases, the other variable increases. So that's the main thing. As one goes up, the other goes up. Negatively associated, similar. Two variables are negatively associated if whenever one variable decreases, the other decreases. So we've got some more examples, and then here we start showing you how to compute R. Now this is a very intricate, detailed, complicated calculation. This is not something that I do by hand. I don't recommend that you do it by hand. Use technology. There's so many computations that go into this calculation. There's so many places that you can make an error. So, but I'll just explain what this is. So you have two sets of data. You will take what we call the response variable and the explanatory variable. You're going to find the mean and standard deviation of each of those. You're going to take each individual response variable, subtract it from its mean, divide by its standard deviation. You're going to take each individual explanatory variable, subtract it from its mean, and divide by its standard deviation. Each of those you're going to multiply together and get some sum, and then you're going to add them all up. You'll get a product when you multiply them and add them all up, and then divide by n minus 1, how many data points. It's a lot. Here's an alternate definition, but we're going to use the calculator to compute these. This is a table or a chart that tells you about the properties of correlation. So these are also good to have in your notes. So linear correlation coefficient. it's always going to be between -1 and +1. So that means -1 on the left most end and +1 on the right most end. If R is +1, there's a perfect linear positive relationship. If R is -1, there's a perfect negative linear relationship between the two variables. The closer R is to +1, the stronger the evidence of a positive association. The closer R is to -1, the stronger evidence of a negative association between the variables. If R is close to 0, then there's little or no evidence of a linear relationship between the two variables. So R close to 0 does not imply no relation, just no linear relation. The linear correlation coefficient is a unitless measure of association. So the unit of measure for X and Y play no role in the interpretation of R. And then the correlation coefficient is not resistant. Therefore, an observation that does not follow the overall pattern of the data could affect the linear correlation coefficient. So it's not resistant to outliers. So here are some more scatter diagrams that kind of give you some R values computed at the bottom. So first one, perfect linear, R is 1. The next one is strong positive linear, it's 0.9. This one is a moderate positive, so trending upward. You got 0.4. The fourth one is a strong negative. E would be a strong negative. It's 0.9 negative. F is a moderately negative, a negative 0.4. A G has no relation. They're just all over the place, no pattern. And then H is not linear, so it's going to be close to 0. We got some more figures, and it says compute and interpret linear correlation coefficient by hand. We will not be doing this. Again, it's very complicated. We're going to let the computer and technology do that for us. But they're kind of explaining step by step what you would need to do. And they give you like some little examples showing you those computations when you multiply those products, sum up all of those products. So this is not bad with 5 numbers, or it's not as bad as it could be, but you find the mean and standard deviation of both of those. They don't show that part, but they're explaining it up here that they found it. Then once you find those, you take each one, subtract the mean, divide by standard deviation, you get a value. Do that for both data sets, multiply those two numbers together, you get this list of numbers. You add up that whole list of numbers, you get this value. And then you divide by n minus 1. So n is the number of data values you have, which would be 5, minus 1 would be 4. So you divide that by 4. And this is what you would get. But the computer will do that in moments, mere seconds for you. So here is the computer example of showing how to compute the correlation in Excel. But at the end, they also show you how to do it in the program that we have in MyStatLab in the calculator. So this one is testing for linear relation. So it says determine the absolute value of the correlation coefficient. We're going to find the critical value from table 2 in appendix A. So there's a table in the back of the textbook that we can look at that will give us one from the sample size. And then we're going to find the absolute value of the correlation coefficient. If it's greater than the critical value, then the linear relationship exists. Otherwise, no linear relationship exists. So using the golf example, staying with that one, we had an R of 9.39. Table 2 in the back of the book shows n equals 8. So you had this critical value, and then because this value is greater than the critical value, we say that there's a positive linear relationship. So the difference between correlation and causation. So where's the good observation we cannot conclude? So correlation between teenage birth rate and homicide cannot conclude. I'm looking for the summary of it. Okay, so basically correlation just means that there is some relationship between the two. So for example, like the number of miles on a used car and the price of the used car, the miles that the car has been driven can affect the price, but it does not cause the price to go up or down, because you can have two cars, the same mileage, but they might have different prices based on the condition. One might be a few years older, so there's other variables that can affect. So while it does affect or has some implication on one of the variables, it does not cause it to happen. So correlation just means there's a relationship that exists. Causation means it directly causes that to happen. So that's a general idea of correlation and causation. Then you have another little example that kind of talks about the lurking variables. It says a lurking variable is related to both explanatory and response. For example, air conditioning bills increase, so does the crime rate. That does not mean that folks should turn off their air conditioner so that crime will decrease. So let me just say this is a lurking variable. Sometimes there could be a positive relationship, but it doesn't mean that one of those causes the other to happen. It just might be just a weird scenario that they happen to have a linear relationship, but not really causing that to happen. So here's another example that fits the one that we were talking about with the lurking variable. Kind of read through that, and then at the end we have step-by-step how to use the technology to do scatter diagrams, and then I'll show you how to compute R. They show you with Minitab as well. And I think they show you also with StatCrunch in Excel. So it shows you several different options that you can use to find and play with those things. So check those and then use the one that you like the best. All right, so at this point, we're going to jump on over to my MATLAB and work some examples.